So what dictates where you are on the main sequence? So obviously it's your temperature and brightness. It's really your mass, all right? A star's mass is the single most important indicator for what its life cycle will be, all right? If our sun had a greater mass, it would be further up here on the main sequence, all right? And think of it, the more mass you have, the more hydrogen fuel you have, obviously because you're bigger, but the more mass you have, the quicker you go through your fuel. So larger stars go through the life cycle faster than smaller stars. So our sun will last about 10 billion years. A star that's smaller would last longer. A star that's bigger would last shorter before it goes into its next phase of its life cycle. The next phase of a life cycle for our sun, which is a low mass star. So here's the deal. So this, you can read volumes about how this process works. The reading went into excruciating detail. But once our sun starts depleting its hydrogen fuel, a star that its main sequence is using hydrogen as fuel, it's using hydrogen into helium. That's what it's doing, all right? Once the helium runs out, all right, think of it as, I don't want to say there's less fusion going on, but once the hydrogen runs out, the red arrows going out go down, and gravity overwhelms the star, and the star basically collapses, all right? When the star collapses, the core gets smaller, which means it gets hotter due to friction. And when the core gets hotter, it means the outermost layers kind of blow off, all right? And that becomes a red giant. Our sun will one day become a red giant, and when that happens, the size of our sun will swell to about the orbit of Jupiter. So Earth will be toast. Literally, it will be toast. And that'll be in about 5 billion years, 6 billion years or so. So it's weird because, fusion doesn't stop, but hydrogen fusion stops. The star gets smaller, then it gets bigger because the outer layers get hotter. Our star is not big enough for that to be a massive explosion. It's just kind of like a swelling. So there's no supernova for our sun. It's not big enough. It just expands to a much larger size. So, a red giant is cooler. It's not that it's cool, think of it as the temperature of the sun is now, just bigger. So I can't talk. Per like square centimeter, the star is cooler because it's energy over a bigger surface area. So it will appear red in the sky. The core, however, is very, very hot. The core might be hotter than the core was originally, but overall the star is cooler because it's more spread out. All right. Now, so our sun becomes a red giant. Red giants are here. All right. Our sun will one day leave the main sequence and it will go up here. So then what happens? Well, fusion hasn't stopped. Helium can be fused into carbon. It's harder and harder to fuse bigger elements. Once you get to iron, you can't fuse anymore. Iron's like the end of fusion for a star. So at that point, fusion's done. But here, once you're a red giant, you're fusing helium into carbon. So that's going to go on for however many millions, billions of years. Now, those outer layers, the star doesn't have that much more mass to it. It's just gotten bigger. So its gravity is sort of diluted. So the outer layers eventually just kind of dissipate away. And all that's left is a white dwarf star, which is basically the core. A white dwarf star, people nickname them diamonds because they kind of are diamonds. It's mainly the carbon that's left behind. Remember, you can fuse helium into carbon. And diamonds are just carbon. Diamonds are crystallized carbon, right? So it's like a diamond in the sky. There's songs about this. At that point, fusion has stopped. In a white dwarf, there's no more fusion. There's no more elements that will fuse, but it's still incredibly hot because of all the heat that it's built up. And over time, white dwarfs just radiate out all the heat, where what's theoretically left is called a black dwarf. And this has never been observed. The time that it would take a white dwarf to completely cool down is longer than the universe is old. So it's just a theoretical construct, the black dwarf, that's the remnant of a white dwarf that's totally cooled down, and it'd be like a diamond in space that's no longer radiating heat, so it's cold. It's a black dwarf. It's kind of cool to think of. Be worth a lot of money if you could get to it. Okay, so that's the deal with an HR diagram. This picture or this diagram is kind of cool. So we talked about what will happen with an average star. So a stellar nebula. So stars begin as clouds of dust that condense. Stellar, as in stars form inside nebulas. Once fusion starts, you get an average main sequence star, becomes a red giant. A planetary nebula. So remember how I said the outer layers of a red giant just eventually escape? So a lot of times you'll see nebula in space with stars at the center. These were called planetary nebula when they were discovered because people thought the things in the middle were planets, but they're not, they're stars. So the name should have been changed, but the name has stuck. So a planetary nebula is just the remnants when the red giant's outer layers escape and you have the white dwarf in the middle. Once the outer nebula gases all escape, what's left is just the white dwarf. So this is what our sun will do, okay? Now, stars that have a massive enough size will go supernova. And the deal here is when, going back to this diagram, when gravity takes over, there's books about this. You can read this in way more detail. Basically, that collapse is so violent that the star kind of explodes in what's called a supernova explosion. There's a special kind of electron degeneracy thing that goes on where normal matter doesn't exist. It's meta. I told you we were getting meta. Supernovas, we'll come back to them in just a minute, have been observed over human history. There was a famous supernova during the era of Kepler that they observed in Galileo. After a supernova, once that's finished, what's left is either a neutron star, which we'll come back to, or a black hole. And black holes are super interesting things that we'll talk about in just a minute. Okay? All right, so this is I was Googling this and found this diagram. This just shows sort of different life cycles of a star. And notice, it calls these stellar nurseries because they're where stars are born. Isn't that cute? So as we go up here, the stars are getting bigger. So our sun's a medium to small size star, and it will go through the whole red giant, planetary nebula, white dwarf phase. Stars that get bigger, obviously they're hotter, and the bigger stars are what will become supernovas. One thing also to recognize is when supernovas, or actually when any star gives off the outer layers. Remember back when we were talking about interstellar winds and particles they're bombarding our solar system from space, and I was like, where do those particles come from? I'm not sure where they come from. Well, they come from the remnants of stars that exploded in ancient times, right? That matter goes throughout all of interstellar space, and some of it could form new stars. Some of it's bombarding the Earth or the solar system right now. Now, one thing that's kind of cool to think about, actually, but before we say that, so in 1987, there was a supernova observed in the sky. It was only seen in the southern hemisphere, and it was called, it was the first one observed in 1987, which is why the name, so supernova 1987A, in case it was going to be a B, I guess. And you could see it with the naked eye in the southern hemisphere. This is, I'm making a quick link to a site on NASA's website. This is a star that was located, the large Magellanic cloud, I can never pronounce that word correctly. Magellanic cloud is in a different galaxy. It's a galaxy sort of neighboring the Milky Way galaxy. And the star that made this supernova went supernova, I think 160,000 years ago. So when humans were wandering the plains of Africa, the savannas of Africa, it took that long for the light to actually get to Earth, and to where you could see it visibly in the sky in 1987. This is a little animation that NASA put together a couple years ago, where they just they do different composites and zoom in. I'll just let it run. There's no sound on this anyway. What you start to see are sort of like the circular shock waves of matter that blasted from the supernova, and you can kind of see the core in the middle. Here it is right there. You could see it with the naked eye. I mean, I was 7. I don't remember this happening, but you couldn't see it from the northern hemisphere. That's a great picture. I don't know if this is the Hubble Telescope. Yeah, this is from the Hubble. This is a sort of time lapse from the Hubble, showing over the course of years the sort of disk of ejected material getting brighter. It's super cool. So supernovae have been observed in human history. Remember we did the crawl of the crab activity, and we calculated the crab nebula, gosh, formed, it's about 1,000 years ago, the year like 1156 or something like that. And that there was a supernova observed that formed the crab nebula. Ancient like Chinese and Japanese, and I think Arabic records record that, people seeing it in the sky, even during the daytime. But the nebula, the crab nebula, is the remnant that formed from that star going supernova. Okay, cool. So this is a quote from the author of your book. So sometime after the Big Bang, you get hydrogen and helium, you get very, very light elements, but heavier elements like carbon only form in the furnaces of stars. The only way to form carbon is to have helium fuse into carbon in a star. And your body is based upon carbon. Heavy elements like iron or gold or metals form from stars, maybe even from stars going supernova. So if you have a ring that's gold, or if you have iron, I mean, there's iron in your hemoglobin, there's carbon in your body, all of those elements were formed inside stars. So the idea, there's a famous poem called "You Are Star Stuff" by Carl Sagan, that the matter in your body was once part of a star. This is a quote from the author of your book. If you pause to reflect on your origin, it's as amazing as any tall tale told around a campfire. Our bodies, the iron in our blood, the oxygen in our lungs, the calcium in our bones, and the carbon and nitrogen that forms our genetic material are formed from the detritus of generation upon generation of stars that lived and died before Earth was born. The atoms in the jewelry that we adorn ourselves with, gold and silver and platinum, are glittering relics of long-gone supernovas. So you're literally the stuff of stars. It's just got kind of cool thing to think about. Okay, so, that was a lot of rambling. Actually, we need to discuss black holes and wormholes. So something else that Einstein theorized and was right about was that, we know that the more gravity an object has, the more mass an object has, the more gravity it has. The sun's got more gravity than the Earth because it's got more mass. The sun's got more gravity than you do, although you have gravity because you have mass. The moon has less gravity than the Earth because it's smaller. Obviously, the moon's closer than the sun, so the moon affects our tides in ways that the sun does not, just because it's closer. But gravity also impacts light, and light going past large gravity sources will bend. Okay, which is weird because light's just energy supposedly, but light actually does have particle-like characteristics to it. So what if you had an object? What if you had the collapsed core? Let's go back to this one. The collapsed core of a star, where all the matter collapsed into such a small area where the gravity was so strong because you're so close to it where even light cannot escape. And that's called a black hole. Black holes do exist. They were theorized, they've been discovered. Black holes, this picture is from Interstellar, the movie, which we'll get to in a minute, are basically the collapsed cores of massive stars where the matter collapsed into such a small volume that even light cannot escape its gravity. Now, what would happen if our sun became a black hole? Obviously, there'd be no light in the sky, so that would be a problem. But we would, if the sun became a black hole, does that change the amount of matter in the sun? No, it doesn't. It's the same amount of matter. So the gravity is the same. Our distance to it would be the same. So we would orbit the black hole that was our sun for all of time, right? Of course, Earth would be, there'd be no light, so we would all be dead, but the gravity would not change. Now, the difference though, so the idea that black holes like suck everything into them, that's not exactly true. You can orbit a black hole, but the thing is, because they're smaller, you can get closer to them, and the closer you get to the gravitational source, the stronger the gravity is, okay? So if you were, if our sun were a black hole and you were a mile from it, you would have intense gravity. If you were a mile from the center of the sun now, you would be toast, right? So the idea is you can get closer to it. And because light interacts with matter and gravity, you get to a point called the event horizon, which is like a boundary where even light gets sucked into it. So if light gets sucked into it, you can't see it. Now, can you be inside a black hole? Yes, you can. Is there matter in a black hole? Yes, there is, but there's no way to detect it because like I see things because light bounces off them. So they're, in terms of their color, they're black. But you could be inside a black hole. Now you would be dead because the gravity would be so strong it would tear your body apart. But there could be matter inside a black hole. Well, there is matter because things do get sucked into a black hole. How do we know that they're there? Well, things can orbit a black hole, and we've seen things orbiting dark regions in space. But more importantly, as matter gets sucked into a black hole, which as you can imagine is a very high energy event, normal matter gives off X-rays, and X-rays is like a shouting out into space as you get sucked in. And we've seen objects in space that are black that are emitting sort of X-ray signatures, which indicates matter is being sucked into them. So you can see the effects of black holes, but you can't see the black hole itself. But we know that they're out there. This is the movie Interstellar depicting this was the scene, you've seen it where this was a planet that's orbiting a black hole, and the gravity on the planet is incredibly strong because you're so close to a black hole. I want to end with this idea. So another of Einstein's ideas was the notion of space-time, that space and time are connected. And this is getting into Unit 6, so I don't want to spoil it. But he compared space or space-time as to like a piece of fabric. And if you have a piece of fabric just laid out flat, there's no curves in it, it's just flat. But if you put marbles in the fabric bends inward, it like has a little bow in it. And gravity is basically like the fabric of space-time that's being like pushed down by a matter source. So here you see a picture of the Earth, and the Earth is bending space-time because the Earth has, has mass, so therefore it has gravity. This picture, so here you see the sun curving space-time. A white dwarf has more matter, more gravity, neutron star. A black hole, basically, it's the idea of gravity being kind of like a well in space-time called a gravity well. And the size of the gravity well is dictated by the amount of mass of the object. This picture, approximate size of Earth, if it collapsed into a black hole, it would weigh the same as Earth today. So if I took Earth and compressed it into a size, I mean, I know this is projected, but this circle is 0.7 inches. So it's actually not quite that big on my computer screen, but say it's 3/4 of an inch. It would have the same mass as the Earth, just a much smaller volume. So the gravity, if I was this far away from the Earth at that size, the gravity would be very, very intense. And so you'd be bending space-time more the more gravity you get. And usually at some point in class, someone brings up the idea of a wormhole. And a wormhole is the idea, so say that I have two distant regions of space. Worms dig holes in the ground. And you have an object of sufficient gravity where you basically have a dip into space-time. And if I had two dips in space-time, two very distant regions of space that end up connecting, and you could go through it, which obviously would be, I mean, these are theoretical. No one's ever discovered a wormhole. You could get to very, very distant regions of space, like a shortcut. Like picture a balloon you blew up and you put your fingers on opposite ends and push them in and you end up touching, right? Those 2 points were very, very, very far away. There was a great analogy in the movie Interstellar where the guy takes up a piece of paper and folds it. If we were in class, we'd actually be watching the movie, which I wish we had time to do that. Anyway, you know, where if you went through it, you'd be on very, very distant objects or spaces on that balloon through a wormhole. That's the, you know, science fiction loves wormholes, Star Trek or Star Wars, to go through wormholes to get to distant places in the galaxy or other galaxies to basically like a shortcut. Okay, so that was a lot of rambling about wormholes and gravity and Einstein and the speed of light and stars. But I think that's a good place to stop. All right, awesome. I will see you next time.